March 28, 1979, 4 a.m. Inside the Unit 2 control room at 3 Mile Island, the reactor is running at 97% of rated power. The night shift is completely routine. A minor trip occurs in the secondary loop. Condensate polishers fail, halting the flow of feed water. With nowhere for the reactor's heat to go, pressure builds, and the system automatically scrams. Control rods drop, and the nuclear chain reaction stops. At 10 seconds, the incident reaches its projected end. The valve has been commanded to close, but it remains open, beginning a hidden crisis that will last 142 minutes. This disaster starts with a small lamp on a vertical panel near the supervisor's console, a simple status indicator the operators have been trained for their entire careers to trust. Industrial danger often stems from a perfectly functioning indicator telling a coherent, devastating lie. After the partial meltdown, John Kemeny leads a commission to identify the root causes of the failure. The commission finds no single villain. They do not find a single improperly wired component in the control room. The plant was built exactly to specification. Every indicator operated entirely within its engineered parameters. The failure originated in an epistemological gap between the machine and the operators. The system was designed to measure electrical proxies rather than physical reality. Water in the primary loop is kept at 2200 psi to prevent boiling. At the top sits the pilot-operated relief valve. When pressure hit 2255 psi, its pilot stage lifted, dumping coolant. Pressure normalizes, but the valve stem remains jammed open. The entire primary loop is now connected to an atmospheric tank inside containment through a pipe roughly 2.5 inches across. 2,800 pounds of radioactive coolant pour out of the system every minute. This loss of coolant was survivable. The plant's high-pressure injection pumps immediately started pushing replacement water into the loop. The crisis continued only because the operators believed the leak had stopped. The operators monitored a specific status lamp on their console. They had been trained to view this light as the definitive indicator of the valve's position. 10 seconds after the trip, the control system removes the electrical signal telling the valve to stay open. Right on schedule, the status lamp goes dark. The engineering flaw lies in the wiring. The lamp is wired to the solenoid's electrical circuit, not to the mechanical valve stem itself. When the computer sends the close command, the lamp turns off, while the valve on the right remains physically open. During construction, a direct positive position sensor on the valve stem was considered. Engineers omitted it to save time on the building schedule. The plant possessed no hardware capable of telling operators what the physical valve had done. It could only report what the computer asked it to do. Verifying an electrical command is distinct from verifying a physical state. Conflating the two conceals the ongoing mechanical failure, leaving the operators to believe the valve is shut while coolant floods the containment floor. Inside the reactor vessel, the hidden leak causes total system pressure to fall rapidly. Once pressure drops below the saturation point, the physical state of the coolant changes. The liquid water surrounding the fuel rods flashes into steam voids. These newly formed steam bubbles require exponentially more volume than the liquid they replaced. In this closed loop, that rapid expansion has to go somewhere. The steam voids displace the remaining liquid coolant, forcing it upward into the tall pressurizer vessel. The total mass of water is critically dropping, but due to steam expansion, the pressurizer volume is rising. The control panel features a pressurizer level transmitter, calibrated strictly in inches of water column. This is a measurement of volume. The operators watch this pressurizer gauge climb toward the top of the scale. On the right, the underlying math shows that volume is increasing precisely because mass is dropping. The operators interpret this rising volume as an overfilled system. They fear a hydraulic lock that could damage the reactor's piping. To prevent this, they manually throttle the high-pressure injection pumps, reducing the flow of fresh makeup water entering the loop. By relying on volume as a proxy for mass in a boiling system, they were actively starving a nuclear core that was physically uncovering. At 6:20 in the morning, a shift change brings a new supervisor into the control room. He looks past the existing mental model and checks the temperatures on the relief valve discharge line. At 6:22, he orders an operator to close the backup block valve. The leak is isolated, 142 minutes after it began. The control room does not yet understand the severity of the damage. During those 142 minutes, the core has been overheating. Zircaloy cladding reacted with steam, exposing fuel pellets. 62 tons of uranium dioxide and metal melted. 19 tons of that molten material relocated to the lower plenum. The containment shell held, preventing immediate fatalities in the community. However, the billion-dollar reactor was permanently destroyed by an information failure. The regulatory fallout forced the nuclear industry to redesign how reactors communicate with humans. The fleet was backfitted with positive indication valve stem sensors and independent inadequate core cooling meters. These instruments were designed to measure ground truth parameters, physical inventory, and mechanical position, rather than electrical proxies. An instrument is a sentence about the world. Its verb can be accurate, while its subject is false. The lamp at 3 Mile Island was accurate about an electrical signal, but false about a valve. System adequacy exists in the gap between what the machine displays and what the human must know to survive. On March 28, that gap was large enough to destroy a reactor.